Welcome to a webcast made by the Learning Enhancement team based in the Dean of Students office at the University of East Anglia. This webcast is part of the Steps into Calculus series and concerns definite integrals. This guide shows you how to calculate definite integrals and how this can be used to find areas on graphs. Introduction. The important mathematical subject of calculus comprises differentiation and integration. The study guide, What is Integration?, describes two types of integration, definite integration and indefinite integration. These two types of integration are related, but there are some important differences. Most importantly, the result of a definite integral is a number, whereas the result of an indefinite integral is a function, with a constant, usually given by c, added to it. You should read the study guide, What is Integration?, to help you understand the terminology and notation used in integration. A definite integral looks different to an indefinite integral because it is written with two numbers, one at the top and one at the bottom of the integral sign, which are called the limits. When evaluating definite integrals, you first perform the integration as you would do for indefinite integration, but then you input the limits into the answer. So, with definite integration, an extra step is required. Some basic techniques for finding indefinite integrals are given in the study guides: integrating y equals ax to the n, integrating basic functions, integration by parts, and integration in the natural logarithm. This study guide shows you how to substitute limits into the definite integrals and how to evaluate the result in mathematics. It also shows you that you can use the result of definite integration to find areas on graphs. How to evaluate a definite integral. There are four steps needed in order to evaluate the definite integral of a given function, f' of x, between the limits of x equals a and x equals b. Method to evaluate the integral between a and b of f' of x dx. 1. Integrate the function using indefinite integration to give f of x. 2. Put this answer and the limits in square brackets, like this. 3. Evaluate the function at these limits to give f of b and f of a. 4. Compute f of b minus f of a to give the value of the definite integral. In order to understand how to perform definite integration, you should understand each step of this method. 1. First you perform the indefinite integration. The derivative of the function f of x can be written as f' of x. So, as indefinite integration is the inverse of differentiation, the function f' of x integrates to f of x plus c. In other words, the integral of f' of x dx equals f of x plus c. The plus c is not needed for definite integration, and so you just need the f of x part. 2. The result f of x is put into square brackets, and the limits are written at the top and bottom of the square brackets like this. You should notice that this new piece of notation has no integral sign, as the integration has already been performed, but the limits are still present as you have not used them yet. 3. To compute the value of the definite integral, you substitute the upper limit into f of x to give f of b, and the lower limit into f of x to give f of a. You should read the study guide Using Functions to help you with substituting limits into functions. 4. Subtract f of a from f of b to give f of b minus f of a. This is the answer. You can write this process mathematically as the integral between the limits a and b of f' of x dx equals f of x in square brackets between the limits of a and b, which equals f of b minus f of a. Example. Evaluate the definite integral, the integral of x squared between the limits 1 and 2 with respect to x. This piece of mathematics can be interpreted as the definite integral of x squared between the lower limit of x1 and the upper limit of x2. The function you are integrating is f' of x equals x squared, and you can use the power rule for integration to perform it, and so f of x equals x cubed divided by 3. You do not need the plus c. 2. Putting the result from step 1 and the upper and lower limits into this gives the integral between the limits of 1 and 2 of x squared dx equals x cubed over 3 between the limits of 1 and 2. Step 3. You now need to evaluate the function f of x equals x cubed divided by 3 at the lower limit of x equals 1 and the upper limit of x equals 2. Specifically, for the upper limit, f of 2 equals 2 cubed divided by 3, which equals 8 divided by 3. For the lower limit, f of 1 equals 1 cubed divided by 3, which equals 1/3. The answer is given by f of 2 minus f of 1. f of 2 minus f of 1 equals 8/3 minus 1/3, which equals 7/3. So the value of the definite integral is 7/3. This can be written as the integral between 1 and 2 of x squared dx equals x cubed divided by 3 evaluated between 1 and 2, which equals 2 cubed over 3 minus 1 cubed over 3, which equals 8 over 3 minus 1 over 3, which equals 7 over 3. Example, integrate the function f' of x equals 12 between the limits of 0 and 3. Here the function is f' of x equals 12, the lower limit is 0 and the upper limit is 3. And so you can write the integral as the integral between 0 and 3 of 12 dx. Step 1. f' of x equals 12 integrates to give f of x equals 12x. Step 2. The integral between 0 and 3 of 12 dx equals 12x evaluated between 0 and 3. Step 3. f of 3 equals 12 times 3, which equals 36, and f of 0 equals 12 times 0, which equals 0. Step 4. The integral between 0 and 3 of 12 dx equals 12x evaluated between 0 and 3, which equals 12 multiplied by 3 minus 12 multiplied by 0, which equals 36 minus 0, which equals 36. And so, the integral between 0 and 3 of 12 with respect to x equals 36. The shaded area in the figure above shows the area under the graph of the function f of x equals 12 between x equals 0, x equals 3 and the x-axis. As the area of the rectangle is found by multiplying its width by its height, the area is 3 times 12, which equals 36. In this case, the definite integral gives the area of a rectangle of height 12 and width 3. Interpreting definite integrals as areas. It is true to say that all areas can be described by definite integrals, but not all results of definite integrals are areas. It is important that you understand the difference between evaluating a definite integral and finding an area, as the two are not always interchangeable. Case 1. If the function is entirely above the x-axis within the limits. Definite integrals describe the region between the x-axis, the two limits and the function. If the function is wholly above the x-axis between the limits, then the result of the definite integral equals the area of the region it describes. For instance, in the example above, the shaded region has the same area as the result of the definite integral, 36. The definite integral of a function gives the area between the function, the x-axis and the limits only if the function is wholly positive, i.e. wholly above the x-axis. Case 2. if the function is entirely below the x-axis within the limits. When a function is wholly below the x-axis, its value is negative and, as a result, the definite integral gives a negative result for this region. Consequently, as areas cannot be negative, the definite integral cannot describe an area. However, the positive value of the definite integral is equal to the area. So all you need to do is to change the sign of the result. Mathematically, this is known as taking the absolute value. If the function is wholly beneath the x-axis, then the area between the limits, the x-axis and the function is the positive value of the definite integral. Example: what is the area of the region enclosed by the x-axis, f' equals minus 3x squared, and the limits x equals 1 and an upper limit of x equals 2.5. Here the function is f' of x equals minus 3x squared. The lower limit is 1 and the upper limit is 2.5, and so you can write the integral as the integral between 1 and 2.5 of minus 3x squared dx. Step 1. F' of x equals minus 3x squared integrates to give f of x equals minus x cubed. Step 2. The integral between 1 and 2.5 of minus 3x squared dx equals minus x cubed evaluated between 1 and 2.5. Step 3. F of 2.5 equals minus 2.5 cubed, which equals minus 15.625, and f of 1 equals minus 1 cubed, which equals minus 1. Step 4. The integral between 1 and 2.5 of minus 3x squared dx equals minus x cubed evaluated between 1 and 2.5, which equals minus 15.625 minus minus 1, which equals minus 14.625. So, the integral between 1 and 2.5 of minus 3x squared dx equals minus 14.625. The definite integral has a value of minus 14.625, which is negative. As the region is entirely beneath the x-axis, as you can see from the graph above, then the area is the absolute value of this, which is 14.625. Case 3. If the function crosses the x-axis within the limits. If a function crosses the x-axis within the limits, then a part of the function is positive and a part is negative. The portion above the x-axis contributes a positive value to the definite integral, and the portion below the x-axis contributes a negative value to the definite integral. These will cancel each other out to some degree, and so you cannot use the result of the definite integral to find the area. What you need to do is to break down the integral into portions which are always above or below the axis, and evaluate these integrals one by one. To find these portions, you need to find the points where the function crosses the x-axis. These are called the roots of the function, and these form the new limits of the definite integral. For this, you need to be able to sketch the graph of the function. See study guide, sketching a graph. Example: find the area between the function f' of x equals x minus x cubed, the x-axis, and the limits x equals minus 1 and x equals 1. If you directly calculate the integral of the function between the limits minus 1 and 1, you get the integral between minus 1 and 1 of x minus x cubed dx equals x squared over 2 minus x squared over 4 evaluated between minus 1 and 1, which equals 1 squared over 2 minus 1 to the 4 over 4 from the top limit minus 1 squared over 2 minus 1 to the power 4 over 4 from the bottom limit, which equals 1/2 minus 1/4 minus 1/2 minus 1/4, which equals 1/4 minus 1/4, which equals 0. which seems to suggest that the area under the graph is 0. However, the graph below shows that this is not the case. To find the area, you must calculate the definite integral for the parts of the graph above and below the x-axis separately. The part of the function above the x-axis is between x equals 0 and x equals 1. Using these as limits gives the integral between 0 and 1 of x minus x cubed dx equals x squared over 2 minus x squared over 4 between the limits of 0 and 1, which equals 1 squared over 2 minus 1 to the 4 over 4 from the top limit x equals 1 minus 0 squared over 2 minus 0 to the 4 over 4 from the bottom limit x equals 0, which equals 1/2 minus 1/4 minus 0, which equals 1/4. The part of the graph that is below the x-axis is between x equals minus 1 and x equals 0, and so the integral between minus 1 and 0 of x minus x cubed dx equals x squared over 2 minus x to the 4 over 4 evaluated between minus 1 and 0, which equals 0 squared over 2 minus 0 to the 4 over 4 from the top limit x equals 0 minus 1 squared over 2 minus 1 to the 4 over 4 from the bottom limit x equals minus 1. This equals 0 minus 1/2 minus 1/4, which equals minus 1/4. These two results show that the definite integral of the part above the x-axis gave 1/4 and the definite integral of the part below gave minus 1/4. So, when the definite integral was evaluated between x equals minus 1 and x equals 1, the two results cancel each other out. To find the area, you can treat the result of the definite integral for the part of the graph wholly above the x-axis as equivalent to the area of that region, 1/4. However, you need to take the absolute value of the region wholly below the x-axis, and so the definite integral result of minus 1/4 equates to an area of plus 1/4. Adding these two results gives a total area of 1/4 plus 1/4, which equals 1/2. Further guidance and information. If you have any further questions about calculus or would like to discuss any other aspects of mathematics, you can talk to your lecturer or personal advisor or make an appointment to see a learning enhancement tutor in the Dean of Students office. Telephone 01603 592761. Email dos.help@uea.ac.uk or visit our website at www.uea.ac.uk/dos/let. There are further resources on many other aspects of calculus, mathematics, statistics and science available from the Dean of Students office and on its website. These include questions to practice, model solutions and webcasts illustrating essential skills.